Okay, thank you very much. Yep, so this is some work I've been doing during my PhD, which has been supervised by Ted Johnson at UCL. So I'm going to start with this picture, which very nicely illustrates two things. So this is a picture of the Elwha River in the USA, and there was a hydroelectric dam here for quite many years. And in the mid-2000s, they removed this dam, and all of the silt and the sediment that was behind the dam was released along the river and into the ocean. And so this picture illustrates two things. It illustrates, first of all, why you might want to study what happens when a river flows into the ocean, because as we can see here, there's a lot of sediment, and rivers can carry sediment and pollutants and nutrients, and we want to understand like where they're going to go, how far into the oceans they're going to spread, and sort of what scales they're going to decay on. And this picture also illustrates a very typical behavior at coastal outflows, which is you have this strong asymmetry caused by the Earth's rotation and the Coriolis force deflecting water to the right. And you have this coastal current which propagates to the right in the northern hemisphere and would to the left in the southern hemisphere. So this is a particular river, and this is a cartoon from a review paper by Horner-Devine in 2015, which they called A Menagerie of Outflow Types, which shows that there are many, many different qualitative behaviors that occur at different rivers. And that's because there's so many different physical processes going on. You have the influence of topography, of mixing. You have temporal influences like tides and winds and things like that. And so any kind of river can exhibit different behaviors throughout the year and throughout the season, throughout time. And different rivers have many different behaviors. So it's a very complicated problem with lots of different physical processes and different scales going on, and that makes it very interesting and rewarding to study. So there's been plenty of numerical work looking at lots of these different features and trying to investigate their effects, but there's still a need for a strong theoretical understanding to try and unify the different effects and highlight the underlying dynamics. So today I'm going to present to you a model which investigates one of these effects, and that's the role of potential vorticity gradients. So a very brief refresher on conservation of potential vorticity. It's basically angular momentum in 3D. If you have a column of rotating fluid, such as this one here, and it increases in depth, then to conserve volume, it has to shrink, has to get thinner. And as it gets thinner, it spins faster. And vice versa, if a column gets shallower, it gets fatter, and it spins slower. So this is the expression for this conserved quantity potential vorticity. So h is the depth of the column, f is the Coriolis parameter that measures Earth rotation, and zeta is the relative vorticity. So how does this manifest itself in an outflow? Well, if we have fresh river water lying above salty seawater, and our fresh river water comes out the river and into the ocean, and if for some reason this fresh layer gets deeper as it comes out, then that causes an increase in zeta, the vorticity, and drives the current out of the page. And vice versa, if the fresh water, for some reason, the column shrinks, then it will drive a current into the page. So stretching columns goes this way, shrinking columns goes that way. So we want to develop a model that highlights this. And so what we do is we take a shallow water model with a thin, fresh layer on top of a dense, inactive, deep layer. And we have a vertical coastline. And into that vertical coast, we put a source of finite width and finite depth. And we have a steady flux of river water coming out of here. And the key parameter that's going to control whether these columns stretch or shrink and which way the vortical current turns is the ratio of this source depth to this upper layer depth. So initially, we have a uniform upper layer of depth h0, and then we turn on a river coming out of a source of depth hs. And if h0 is greater than hs, then as the river comes out, the depth of the water will increase, and that will drive fluids in the positive x direction. And if H0 is less than HS, then it will drive fluid in the negative x direction. So I should mention here the previous work done by Kubikawa in 91 and Johnson in 2017, which looked at the limit of small depth differences. And we're going to extend that to order 1 depth differences. OK, I also mentioned earlier this Coriolis force, which deflects water to the right-hand side in the northern hemisphere. And that is called a Kelvin wave. And that's what happens when you stir a cup of coffee. You get like the coffee pushes up against the boundary of the cup and deepens. And so we have this Kelvin wave, which always pushes in the same direction, which is positive x. And that can either be reinforced or opposed by this stretching or squashing of columns. So we have this model. It's this time-dependent rotating shallow water equations, still too complicated for analysis, so we introduce a small parameter, which is the ratio of the offshore to the alongshore scales. First order in that gives us these semi-geostrophic equations, which means there's a geostrophic balance in one direction only. And we can use that, put this into our expression for potential vorticity, solve it, we get a nice ODE, and the whole system reduces to a hyperbolic set of two equations, a nonlinear hyperbolic set of two PDEs, in which the only parameters are capital H, which is the ratio of these two depths, and Q prime, which is a function that we use to prescribe the outflow of the river. So if capital H is greater than 1, then the initial depth of the river water is shallower than the ocean layer, and so it will deepen as it comes out, and we have this reinforcing dynamics. So here's a picture of some results with reinforcing dynamics. So H is greater than 1, and the river water has deepened as it comes out. Blue shows the extent of river water, and black contours are the depth of the river water and the ocean layer. And the source is between these two dashed lines at plus and minus 1. So because in this case of fluid column stretching, both the Kelvin wave and the vortical turning are pointing in the same direction, everything is sending fluid to positive x, and there's no disturbances upstream of the source. We have this steady current forming, and the Kelvin wave, the Coriolis-driven one, is faster than the propagation of the river water and disturbs the fluid downstream, disturbs the fluid ahead of the river water. So, and that's what happens in this case. Our model is simple enough that we can actually give an analytic solution and completely describe the whole flow. And this is one interesting thing that we can highlight is the width of this steady current, as it depends on H, the depth ratio, and Q0, which is the flux of river water. So as the flux of river water increases, the depth of the width of the current increases because a wider current is needed to support more flux. But as the depth of the ocean layer increases, then the width decreases, because if the ocean layer is deeper, then the columns are stretching more, and they will also be deeper, and so that can accommodate more fluid. So we have these kind of competing effects here to determine the width of the current. So now we turn to the case where the columns squash as they leave the river mouth. And for a certain set of parameters, we might get behavior like this, where the width of the current increases indefinitely. As we keep running the integrations, it just gets wider and wider. But we can see here that the Kelvin wave is still driving flow downstream, but now the squashing of the columns is sending some fluid upstream. So now we have a balance between something that wants to send fluid upstream and something that wants to send it downstream. And if we use a different set of parameters, we find that actually now the solution becomes steady after a certain amount of time. And we have this anticyclonic circulation where fluid comes out the river, turns left, and then a portion of it recirculates and heads downstream in the end. And so what's happening here is we actually have a transport of ocean water from upstream of the source to downstream of the source, and propagation of river water in both directions. And again, our model is simple enough that we can explore the full parameter space. What we can understand is that as h gets smaller, so 1 minus h gets bigger, then this squashing effect is stronger, and that balances the Kelvin wave flow and means that we are more likely to have this steady solution. Okay, so I'll just leave you with my conclusions that we've developed a simple model that shows the importance of potential vorticity gradients for order 1 Rossby number, and shown that vortex dynamics can either oppose or reinforce the Kelvin wave. And some vortex squatching is necessary for the upstream propagation of river water. Thank you very much. Yes, we have done some. So it's not quite, the model is a bit too simple for like quantitative comparison because we don't have a density difference between the fresh water and this upper layer. But we have done some comparison with experiments. Here, this is an experiment from another paper by Horner-Devine, and this shows the velocity within the fluid, the alongshore velocity, and we have like good improvements there.
I'm Yong-sung, working at the University of Dundee, and this work was supported by the Royal Society of Edinburgh Scottish Government Personal Research Fellowship, co-funded by Marie Curie Actions, hence the three logos. So the motivation was that we have been using a wave, a specific wave called solitary wave for tsunamis research for a long time, but recent field observation shows that the tsunami is actually much longer, as you can see here. So the red one is the field observation during 2011 tsunami, and the blue one is the solitary wave we have been using if we match the wave height and water depth ratio. The thing is, it's very difficult to make a wave longer than solitary wave. The wave wants to become a solitary wave. It's their nature. So existing wave, conventional wave maker cannot make those long waves. So I had a very simple idea. Instead of having a wave generator at one end of the tank, why don't we just move the entire tank? I was surprised that I was funded, and so I worked on it. So recent publication summarized the results. So some of the theoretical solution, analog solution for the linear theory, and homemade nonlinear solutions are reported in here, and characterization of waves, what kind of wave I can make, are summarized here, and also what happens when those waves arrive at the shore is summarized here. So I'll try to talk about everything. So simplest possible waves. So I move the bottom from initial negative displacement to the flat position, which will make a positive wave, or I start from flat position, move it down, and move it up to make wave led by a trough. It has a name, leading depression wave. It has quite significant. It's significant in tsunamis research because there are these kind of tsunamis, and if it arrives, usually shoreline recedes, and people get interested, so they follow the shoreline. But by the time this positive wave comes back, it's too late. But there were a number of observations of this kind of wave, but it was never carefully studied simply because it cannot be easily made. But it could be made in my wave tank. So you can see these are reflections. So you can see the data and linear and nonlinear solutions. Of course, nonlinear solutions better. And these are the run-up data. So this is the solid lines of numerical the result, and dashed dot is the analytical result, and those are the experiment data. Of course, there's a lot of difference. I'll explain this later on. So long story short, so I can make more realistic wave. So the blue line is the field data, and the red line is the wave that I can make using the kind of wave maker. Comes with warning as long as the wave tank is long enough. But my tank was not long enough, so this was done with a numerical solution using only 1 degree of freedom. So that's a good thing, but we need very long wave tank. So for further discussion, we need a little bit of background, and you might get to know something very useful. So it's called surf similarity parameter. It's a ratio between two slopes. or power of two slopes. So one is the slope on the beach. The plain beach has the slope, and the other slope is the wave steepness. It's the ratio between the wave height to the length. And basically, if the so depending on the ratio of those two slopes, you see different kind of breaking or no breaking, or it is well known that for both regular waves, sinusoidal waves, or solitary waves, there have been a lot of discussions of surf parameter because it's very useful for classifying the type of breaking, as well as the collecting all the run-up data. Run-up is the height of the wave when it arrives at the shore, how far it goes up, and all the data, all the possible data can be nicely collapsed using the similar parameter for both solitary waves and regular waves. So can we do the similar thing with the wave that I can, the new waves, the new longer waves that I can make? And for that, we first have to define the slope of those waves. It's not, the wavelength is not very well defined because it's asymptotically approaching the it's not like a sinusoidal wave. So I define crest and trough, and the ratio between the height and the length is called wave front steepness, and we have the slope for the beach. So those are the wave front steepness for all different cases all the waves that I could make in the wave tank. And then I measure run up on a beach. So the line is the result from shallow water, the nonlinear shallow water equation with moving boundary. So those symbols are the measured data, and the line is the simulation. And finally, collect all the data. You can see somehow the run-up has some trend when it's plotted against the surf parameter. And more nicely, I think there's some sort of criteria between breaking waves, those field symbols, and non-breaking waves. But if we go back to the solitary wave case and compare with it, I'm missing all those data. This requires larger surface similarity parameter, means the milder slope or much steeper wave. Both means I need bigger wave tank. So I'm missing the data, more data here. And also we have noticed that there are difference between the theoretical solution for the run-up and actual data. When I added simple velocity scale type friction factor, I can match the run-up height. But this is the actual data, and these small circles, small dots are the data with some phase shift. So as you can see, when there is phase shift, it seems to match very well. But the phase shift cannot be found in a nice way. Different cases have different phase shift, and I think that's because this friction factor is in fact not a constant, but a function of time and space, which has to be measured. So we need further consideration for this part. So these are the concluding remarks. So the new wave makers, the simple one, can make very long wave. And both run-up and breaking seems to be explained by a kind of surface similarity parameter, just like in regular waves and solitary waves. But I would need more data, possibly need much bigger wave tank, and also more work needs to be done for the friction factor. And for that part, so I made much longer wave tank with 3 degrees of freedom. Remember, I could generate more realistic tsunami waves with enough length with just one moving part. But now I have 3. I just made it. So I'm going to play with it for the next semester, I think. And especially for this one, since I have more degree of freedom, I want to observe the reflected wave. I tried this with older one, but reflected wave, because of the wave dispersion, the nonlinear dispersion, it has smaller length component, which couldn't be observed by the long moving bottom. So that's why I have segments of bottoms. But eventually, this is what I want to make. I was talking about this for a number of years, and finally I have some international partners and discussions going on, and hopefully we can make this one. And in a couple of years, I might be able to talk about this. Thank you very much.
Questions? How big is the tank?
The one I have right now is only 2 meters long, 10 centimeter wide. So it was very difficult to convince engineers to publish my paper. But, yeah. So that's why everything's in terms of non-dimensional numbers. Yes.
So let's thank our speaker.
Okay, thanks very much. So I'm Gregory Lanesurf. This is work really done mostly by Francis Robertson, who's a PhD student here at Manchester, funded by EPSRC. He's now moved to the School of Engineering at Birmingham, where he's doing flow past slightly different obstacles in that he's looking at drag on convoys of trucks as they move down roads. But there are some similarities with what he did for his PhD, but it's his PhD work basically that I'm going to talk about now. Okay, so these are lab experiments. You can come and see the tank if you like. It's in the Paris building just over there. So it's a tank that's about 5 meters long, 30 centimeters high and wide, and we're using it to look at flow past obstacles. In this case, you can see a whole array of obstacles. It suggests here we've looked at 1, 2, and later on many emergent obstacles. So these are obstacles that stick right through the full water depth. You can see here a random array of square obstacles. And we're thinking here of things like flow past vegetation as well as flow past structures that you might make. And there are a number of reasons for that, which I'll come on to in a bit. But as I say, we're using square-shaped obstacles, low Froude numbers, Reynolds numbers, based on the speed of the flow and the size of the obstacles in the range about 5 to 20,000. And 2 sizes of obstacles, 38 or 19 millimeters, or 1.5 and 3/4 inches. And when we're looking at 2 obstacles and trying to measure the flow, the drag on one of them, we're measuring the drag on essentially what we think of as the downstream obstacle. So we measure the drag on the black obstacle here, having placed some other obstacle upstream of it, where Sx is how far downstream, if you like, this obstacle is, and Sy is the lateral deviation. And actually, it was much easier to keep the measured drag one in the same place and move the other one around all over the place, because then you can keep the strain gauge measurements much better. Okay. Before we did one obstacle, we did, 2 obstacles. We did one obstacle. So this is looking at the flow on the center line past the obstacle from about 5 sides upstream to 15 downstream, where U is scaled by the bulk mean flow. So it starts at about 1. It drops down as you get to the front of the obstacle. It goes negative in the weight region in behind, and then it recovers back up to, by the time you get here, getting up to 90% of the original value, which gives us some confidence that we've actually got the whole thing here. So, a matter of interest, we published some results here. This is from Lin et al. A little while ago. I would be worried that their speed doesn't actually recover to the background, anything like to the background case. I should say our tank has quite high turbulent intensities, which is more realistic for environmental flows. Lots of people spend ages making really nice, clean experiments, but actually if you're modeling flows looking at marine current turbines or flow past vegetation or things like that, you actually want quite high turbulence intensities, and of course that affects the way the wakes recover to some extent. The drag coefficient we measure is just the force divided by a half rho u squared times the area facing the flow. And for a single obstacle, we get 2.11, which is what everybody else gets for flow past square obstacles. The nice things about square obstacles, as opposed to circular ones, is that it's pretty independent of Reynolds number. You know where the separation points are going to be. people use circular cylinders to look at flow past vegetation, but I always think that's a slight challenge. Partly, it keeps on changing with Reynolds number. Partly, vegetation isn't really smooth circular cylinders. At best, it's bumpy cylinders, and quite often it's actually polygonal. So actually, these kind of things make a better model because the drag stays much more constant and is closer to 2, which is more like what you actually usually get. Okay, next thing we did was put them, or Francis did mostly, was put them in a tandem pair, so that's one behind the other. So, okay, we have one at the front here, one behind it. First of all, looking at the flow, so if they're close together, this is a spacing of 2.5 sides, and the flow is completely negative in the region behind, so and negative behind here and recovers back here. If you move them far enough apart, so this is 10 apart, then you still have a little negative region here. The flow recovers to, in this case, about 70% of the background value, goes down again and up again. We'll come back to why that's interesting later on. If we look at the drag on what I've called the downstream obstacle, so here we're actually measuring the drag on the upstream obstacle. Okay, so measuring the drag on the downstream obstacle, not surprisingly, it's negative in this region, rises up as you go here, and is higher at the bit in between. One kind of interesting question we had was, and this is what's captured on this slide, is, okay, let's say, well, we know the speed changes because I showed you that before. Let's say if we just worked out the drag based on the flow speed from a single obstacle, how good would that be at calculating the drag that we actually measure in the real case? And the answer is it's actually quite good, so long as you're not very close. So if you're about 4 sides away downstream or upstream, if you just use the velocity you predicted from the single obstacle, that will give you quite a good measure of the actual drag. It's only when you get very close that things get a bit more complicated. And that might be useful when you're trying to put together multiple obstacles, because maybe you can just use some kind of superposition, provided your obstacles aren't too close together. That might be a useful way of modeling things in the future. Okay, side by side. So perpendicular arrangement now. So the flow's coming this way. We're measuring the drag on one of these, and the separation is this. And obviously, we're limited by the size of the tank, which is more cross-sections away for the thinner one, which is this smaller one here, which means we can go further away. And you can see the drag is, not surprisingly, higher when the things occupy more of the width. Okay, so there's a kind of blockage effect here that's important. Actually doesn't change a huge amount. Is kind of highish all the way along. And actually other people have done these two arrangements before. But what we've also done, and this is kind of the kind of key plot really, is having done the kind of tandem, perpendicular one way, side by side, perpendicular the other way, we then did basically all other possible combinations. So this takes a little bit longer. So just to get you clear about what we're looking at here, so when we look at a location, we're measuring the drag effectively on the obstacle here, given that there's an obstacle down here. The reason for this dotted area here is you can't put an obstacle that close because then it would overlap with the first one. So not surprisingly, for obstacles that are immediately behind, as we've seen already, you get low, and if it's really close, negative drag on the one that's immediately behind, and it recovers slowly as you go downstream. All the drag coefficients are smaller, and the recovery is quicker in the case where the obstacle occupies a smaller proportion of the whole channel width. And I think what's particularly nice is the place where you get the biggest drag is actually on an obstacle that's, of these pair, is actually this one that has the biggest drag. So the slightly upstream one to one side. Okay? That's the one that has the biggest drag. And when you think about it, maybe that's not so surprising. I've kind of sketched a little flow line here. If you think about it, the flow accelerates through here. Means the pressure is going to be really low at this point, which means you have perhaps an even lower pressure wake region behind this slightly upstream obstacle than you do behind the slightly downstream obstacle. So actually, it's this one here that experiences the highest drag. And you can see it's about 3.6 in this case and 2.8 in this case as the drag coefficient. So quite a bit bigger. There are other interesting features about what happens as you get nearer and further away from the wall. We have looked at, or Francis has looked at, what happens when you have an array, which is kind of what we were building towards, because we're interested in what happens in where you have an array of vegetation or obstacles, or possibly deliberately placed obstacles, or deliberately placed vegetation for that matter. There's an increasing interest in using wetlands as a way of modifying flood behaviours in upstream areas and catchments. We might talk to United Utilities about doing a bit more work on that. But so simple regular arrays, uniform ones like that, or staggered ones like that, or completely random ones like this. It turns out these all do, despite they're meant to be normally the same kind of random arrays, we got good steady drag coefficients out of these, but different ones for different values. You need really quite a long period of random array to get to a state where you've got a pretty much steady situation. I should say in these cases the flume is sloping. You can make the flume slope so that you have the same depth all the way through, and you've got essentially normal flow with a balance between the drag and the and gravity, which makes it easier to work out. Okay, so right, drag coefficient on a square obstacle is 2.1. We kind of know that already. Largely independent of Reynolds number and turbulent intensity and various other things. Much of the variation of the drag coefficient looking at one obstacle compared with the other could be accounted for if you just kind of worked out the flow field from one and then said, right, let's just use a half rho u squared for calculating it elsewhere, except when you're really close, where things get a little bit more complicated. The biggest drag occurs for an obstacle placed slightly upstream and to one side of the other one. And not surprisingly, all of these things depend on the blockage ratio. Something that we haven't talked about a lot here, but I've said we're trying to simulate realistic environmental flows, and people have found this as well when they're looking at arrays of wind turbines or marine current turbines. It's important to think about how the weight recovery works, because if you get that wrong, I mean, doing numerical experiments, it's really easy to get the drag on the first obstacle right. It's very much harder to get the drag on the downstream obstacle right, and that's because of this issue, I think. That's always been a bit of a challenge. Okay.
Questions?
Oh, well, there are lots of parameters. I mean, as you notice, we also did it all head-on. We haven't changed the angle of attack. So there are quite a lot of other parameters that you could play with. And you're right, having different sized obstacles might be an interesting thing to do as well, yeah. Yeah.
Do you have any, so as I understood, there was a free surface involved.
Yeah.
So do you have any sort of understanding of how much difference like the depth ratio is?
Yeah, so, I mean, we used a number of different depths for the different experiments, and there is some, although it's relatively low Froude number, so there are not big differences in the free surface height as it goes around an obstacle. There is a bit, and that does contribute slightly to the forces involved. So it's not quite like a pure rigid lid type experiment, but those aren't very big in these particular experiments.
Thank you. So hello, everyone. I'm a postdoctoral researcher at Northumbria University, and I'm here to talk about a type of engines which work on the Leidenfrost effect. To start with, what is a Leidenfrost effect? So when the water drop interacts with a surface heated at temperatures above its boiling point, it boils. But if the temperature is high enough, then a film of vapor forms between the drop and the hot substrate. And what that vapor does is that the drop levitates on that cushion of vapor. Apart from giving it high mobility, the film of vapor being a low thermal, having a low thermal conductivity also decreases the evaporation rate of the droplet. Thereby, we see a spike in the drop's lifetime with temperature, and that point is called the Leidenfrost temperature. Now, if we texture the substrate asymmetrically in the form of ratchets, as shown here, drops can self-propel on these ratchets, and if we make them superhydrophobic, then the drops can propel even at temperatures lower than the boiling point of the liquid. And this propulsion happens because when the evaporating vapor interacts with the asymmetry in the substrate, there's a pressure gradient that develops because of the asymmetrical substrate, and the vapor flow is redirected along the slope of the asymmetry, which drags the highly mobile droplet along with it. Now, the same propulsion mechanism can be used to rotate droplets on turbine-like asymmetrical substrates in different modes. And the same phase change propulsion mechanism can also be extended to sublimation, where blocks of dry ice can be seen to rotate on these similar turbine-like surfaces. Furthermore, if we couple this with an electromagnetic generator, like a coil and a magnet system here, we can actually get a voltage out of this rotation. So these experiments kind of provide a concept of a heat engine based on the Leidenfrost effect, where the energy is harvested based on the temperature difference between the turbine and the ambient surroundings, and the rectified vapor flow on these turbines performs the work. The heat cycle here is similar to a Rankine cycle, which is used in steam engines, and the working substance can be any phase-changing liquid or solid, such as water and carbon dioxide I've seen before, or even organic liquids. Now, to realize such an engine, we've seen that a solid working substance can be easily used to couple this rotation with an electromagnetic generator. But to have a continuously operating engine, the challenge is to obtain a closed cycle which can feed in the working substance continuously. So I'm looking at liquid working substances which transfer the torque from the turbine onto a surface tension coupled solid disk, where the main challenge is getting a stable liquid film which can rotate continuously. So the setup that we have is we have a liquid volume levitating over a turbine-like surface, and it's coupled with a glass plate on top so that we can actually visualize what's happening underneath. We also supply this turbine with a continuous feed from a syringe pump, and we monitor the speed of rotation of this disk and the liquid volume water thickness over time. And when we start the rotation, after a few seconds, what we see is that there is a steam bubble that forms here, and which corresponds with an increase in the liquid height that we obtain from the side. And that's because the liquid is pushed out radially and collects in the form of a toroid. And by adjusting the flow rate, we can actually, after some time, get a stable liquid height formation, which indicates that we can operate this engine continuously at a constant volume. On the speed side, we see that the speed increases and then stabilizes at a constant angular speed. And that happens because we have the driving torque, or the rotation is driven by the torque from the vapor flow, and is resisted by an inertial resistance because the liquid deforms over the grooves of the turbine. So analytically, we can get a Tanch curve for the rotation of this disk, and we see that it fits very well with our experimental data. And that also defines two limits. At very long times, we get an constant angular speed given by omega t. And at initial times, we can get the angular acceleration from the slope, which would give us an indication of the torque. So to address the issues of liquid stability, because of that steam bubble formation, what we first try is to change the wettability of the top glass plate. So on the left, we have an untreated glass plate, and on the right, we have a plasma-treated glass plate, which makes the plate superhydrophilic. So we see that in the plasma-treated plate, there's still a very faint steam bubble formed, but still the liquid spreads uniformly. And after some time, we actually see that the plate rotation is much more stable compared to the wobble induced in an untreated glass plate. Another way of trying to suppress the formation of this steam bubble is to change the groove depth or temperature, so as to reduce the pressure that's generated at the center. So we have a groove with a groove depth of 100 microns in this turbine shape, and we see that the torus forms at a temperature range of between 200 degrees centigrades, with different sizes depending on what the temperature is. But if we increase the groove depth, we see that at lower temperatures there's no steam bubble formed at all, but it does form at a higher temperature. Now, reducing the temperature also means that there would be some effect on the speed that we get out of it eventually. So we also look at this variation of the terminal speed with temperature, and we find two regimes, one where the speed increases with temperature significantly, and the other where it stabilizes, almost stabilizes. And this transition can be explained by considering that the liquid deforms over these grooves. So in this region, because the temperature is low, the pressure from the evaporating vapor is low, and therefore the deformation of the liquid is considerable, which levies a strong dependency of the speed on the temperature. At higher temperatures, there's enough pressure for the liquid to be pushed out of the groove, which makes it completely levitating over the entire substrate, and that has a low dependency on the speed on the temperature. And this transition point can also be moved if we change the groove depth. So for a shallower groove, we see that this transition actually happens at a much lower temperature, which also implies that having a shallow groove, we cannot really get a high speed, or the speed saturates after a certain temperature. So in conclusion, we showed the operation of these engines in a batch and continuous mode. We showed that we can operate these engines using liquid and solid substances. Now, these engines, the most of the energy spent is spent in levitating the solid and liquid components. So it's very energetically expensive to operate on Earth. So we are looking at applications in extreme environments, for instance, microgravity conditions in space and planetary explorations, where microgravity helps reduce the weight that needs to be supported, thereby increasing the efficiency of the system. Also, to reduce the energy spent in levitation, we'll also look at energy harvesting at microscales, where when the system scales down, the mass of levitation scales down as well. However, there are still a few challenges in achieving such engines. One is it is highly desirable to have a lower Leiden frost temperature, so that less amount of energy is spent in levitating this block. Development of stable coatings, which are thermally and mechanically stable, is important. Then the asymmetry of the substrate itself leads to extreme thermal gradients on the substrate, which is difficult to image in real time because of the multi-layered system that we have. And that's also important to develop accurate models to understand what the heat and mass fluxes are in order to better design these systems. So I would like to thank EPSRC for funding this project, and we are working with our team in Edinburgh as well. And I'm happy to take any questions for this.
What about the efficiency of these machines? Is that maybe an erratic question to ask?
No, it's a perfectly obvious question to ask, actually. Yeah. So the proof of concept study that we did, the video that we showed for the block of dry ice, given that system, we got an efficiency of around 1e minus 6 at that time. But the thing is that we can increase the efficiency by, again, optimizing the system much better. We have evaporation from the sides, from the top as well, which hamper the calculated efficiency. So better designing the turbines, again, reduce system scales, microgravity conditions would hopefully increase the efficiency significantly on that. Yeah. Okay. Thank you.
Yeah, thanks. So yeah, I'm going to speak about controlling droplets on flat surfaces. So the ability to control droplet on flat surfaces could be very interesting for a range of applications, among which microfluidics, you can think about lab on the ships, analytical chemistry, or bioassay applications. For all those applications, it could be very convenient to be able to put drops on flat surfaces and to be able to position accurately those drops on a certain position, merge the drop with another drop to induce some kind of chemical reaction, then move the whole thing to a different position to do something else. So you have different physical mechanisms you can use to control the motion of droplets. You can use temperature gradient, humidity gradient as well, surface acoustic wave, and you can use wettability gradient. So I'm going to speak about wettability gradient in this talk. So you can see here on the side an example of an experiment that has been done by Lee et al., when you can see a drop moving because of this effect. So basically the wettability is higher in the center of the sample. So if you put a drop on the side, the drop will naturally move toward the center. So one way of creating a wettability gradient is to use textured surfaces. So you take your flat surfaces and put very small pillars on top of it in the order of 10 microns width, roughly. And you put your drop on top so that it lies only on the top of the pillars. And because the drop prefers to be in contact with the solid than in the air, the drop will naturally move toward the regions with the higher pillar density. So if you have like small pillars on one side and big pillars on the other side, the drop will naturally want to move toward the right. So you can see here another example. It's the same mechanism, slightly different configuration. So this is fine. You can move drops using these mechanisms. The main problem of this is that you cannot move drops on a very long distance. And this is because of the pinning effect. As soon as you put a drop on a surface, the drop will be pinned, and you need to exert a certain amount of force for the drop to begin to move. And if this spinning force is high, it means that you need a very high gradient of pillar density to move the drop, which means that you cannot move drops on very long distances. So you can see in this experiment, they use gradient of pillar density going for 0.2 to 1, and they are only able to move the drops on 1 millimeter, which is not a very long distance if you want to perform some kind of chemical reaction or merge this drop with another one. And if you try to move the drop on longer distances, so Shastri et al. Tried to move drop on 6 millimeter, you can see that the drop stay pinned. And this is basically because the driving force, so the light blue curve that you have here, is not enough to overcome the pinning force that you have in blue here. So this is really the main problem of those surfaces that restrict a lot of application. So what we wanted to do is to actually reduce the pinning force so we can extend the possibility of those surfaces. And we wanted to use slip surfaces. So slip surfaces are surfaces that exhibit very low pinning forces. So a drop on the slip surfaces will be very easy to move. So if we can use those surfaces to reduce the pinning force, we should be able to extend the possibilities of the surfaces. So briefly, slip surfaces are inspired from the Nepenthes pitcher plant. So this plant is very slippery inside to catch insects. So if you want to create a slip surfaces, you take a substrate, add a porous layer on it that we imbibe with oil. And if you put a droplet on this surface, the drop will just slide on the layer of oil. So it will be very highly mobile. So we'll try to use that to reduce the pinning force. So the first step was to actually create surfaces with wettability gradient. So this is a diagram of the surfaces we've made. The black part corresponds to the pillars. So you can see we have low density of pillars here, high density, and we have a gradient. This is SEM images of the pillar. We add on top of that the hydrophobic porous layer that we imbibe with oil to make that surface slip surfaces. So the first thing to check on those surfaces is to see if we still have a wettability gradient. And one way of measuring this is to measure the apparent contact angle. So this is the contact angle you have here. So we put drop on the sample for different density of pillars, and you can see that the apparent contact angle reduces with the fraction of pillar. So this is a good indication that we do have a wettability gradient. So that's fine. And the second thing is to check that we actually reduced the pinning force. And one way to measure that is to measure the contact angle hysteresis. So we have contact angle hysteresis below 4 degrees, because it's quite difficult to measure below 4 degrees. And for the previous surfaces, so the non-slip surfaces, they had contact angle hysteresis around 25. So we were able to reduce the contact angle hysteresis by a factor of 5, which is great. So drops on those surfaces should move very easily. That's the point. So we tried that. So you can see here videos of drops on surfaces. So the low regions, low pillar density regions are on the left, and the high density are on the right, and you can see drop moving toward the high regions. So all those videos are done for different gradient of pillar density. So the higher one is this one. We can see the drop moving very, very quickly. And this is like a very low gradient where the drop moves very slowly. So those surfaces are interesting on several points. The first one is that we can apparently tune the velocity of drops depending on the gradient of solid fraction. So for example, if you have an application where you need a drop to have some residence time at a certain point of the surface, you can tune the velocity of the drop using the gradient of fraction. The second point that is interesting is that we can move drops on longer distances. So in those experiments, they were able to move drops on 1 millimeter. If you take this surface that we have here, the gradient is 0.03, which means we should be able to move that drop on roughly 30 millimeter, which is not that long, but is enough to perform some kind of microfluidic application if you want to merge drop, to split drop, etc. And the last thing that is interesting is that we can, the driving force is actually strong enough for the drop to move against gravity. So this is this surface that we just tilted with an angle of 6 degrees, and you can see the drop moving uphill. So we can beat gravity. So this is fine. This is interesting. It would be very convenient now to have some kind of equations to be able to explain what's happening and to be able to help us designing surfaces for specific applications. So to do that, we made a force balance on the drop. So you have different force acting on the drops. The first one is the driving force that we create using the wettability gradient. That is proportional to alpha, the gradient of pillar density, and RB, which is the side of the drop. You have a term of dissipation that will be a resistive force for the motion that is proportional to the velocity, and a term that will be a resistive term that will be linked to the pinning force. So if you have a drop moving at a constant velocity, you can rewrite this equation to have a relationship between the capillary number and alpha, the gradient of pillar density. So this is something we can check experimentally. So we measured the velocity of drops of different size on different gradients, and you can see that we found this linear correlation. The equation were predicted. And if you plot the capillary number against the rest of the equation, you can find that all the points collapse rather nicely together. So we'll still have some work to do with this model, because at the moment we are fitting this dissipation coefficient. So we have to find model to estimate the dissipation to close those set of equations. So just to sum up, we were able to create surfaces with wettability gradient that are able to induce forces on drops, and we were able to reduce the pinning force using those new surfaces called slips. The main result of this is that we have extended traveling distances. We can control the velocity of the drop as well, changing the gradient of pillar fraction, and we can move drops uphill. So I'd like to thank CPSRC for funding this research. Thank you for your attention.
Any questions?
The longest distance was not from the one with the highest gradient.
From the highest gradients.
Highest gradient has the highest speed, but it seems the second one was farther.
Yeah, though I had to stop the videos because it takes quite a long time for the drop to move across the whole sample. But basically, the drops keeps moving at the same velocity until they reach the end. So the problem with this one is that we have a fraction of 0 here and a fraction of 1, which means you cannot move the drop further. So it's quite fast, but you cannot move the drop on a long distance. That's why we're using this one to move drops on very long distance. Thank you.
Sorry. Thank you very much. Seems terrible being a third person in succession from there. But hopefully this will be a little bit different, but it'll pick up on what Gabby said. So my name's Glenn McHale. This work was really done by 2 PhD students in supervision, of course. One was James, the first one. He was the experimentalist. One was Elfigo, who was the theorist. So I'm going to talk about these slip surfaces, which are sometimes called lubricant-impregnated surfaces. And as was said before, the motivation here was pitcher plants. But it's an interesting question about how you get droplets to move on surfaces. We all know that if you look at a small droplet on a window, droplet of rain, it doesn't go down the surface, not if it's small. And so contact angle hysteresis, the stick bit, is pretty strong. And there's really 2 strategies generally in the literature. One is to make a surface that balls a drop up, something like a lotus leaf, Gore-Tex jacket. You ball the drop up, you reduce the contact area, or more to the point, you reduce the contact lines, and then it's very easy to move the droplet. But the other one is if you could get to a perfect situation where you really had Young's law contact angle and droplets moved, then even for a very small tip, then a droplet would move on a surface. A droplet would lean, normally, until the front angle of a droplet goes past the advancing, the back goes past the receding and move. But if those 2 are the same, droplets move very easily. And that's what the pitcher plant really does within there. And the way it's done is you take a surface, you make it rough, you make it hydrophobic, but oleophilic, and you essentially impregnate oil such that the oil completely coats the tops of your features. The roughness holds the oil in, and your droplet then sits on the top, removing the contact lines. Possibly you get a little bit of oil around the surface of the drop if you're not careful. Depends what lubricant you use, but it's really effective. So here's one of these pillar surfaces. We made this one in our lab some time ago. You tilt the surface by less than 1 degree. And that's a droplet sliding at less than 1 degree. And you can see it's on a lubricant because you have some Neumann triangle sort of uplift of the oil at the edges, those little wings that you can see as a whole. So it's slippery because you've converted the solid liquid contact, the solid liquid contact of the droplet into a droplet lubricant contact. And I guess my question is, if you have a super slippery surface, that's great for some applications, but in others what you really want to do is design where things stick. So you want to throw the stick back in to a completely slippery surface. And so how do you do that to get stable positions and to get motion that's directed? Oops, that's gone too far. So here's an idea. Why not use the Cheerios effect to do it? Cheerios effect being talked about, you think of a cereal bowl, put 2 Cheerios in, they clump together. Or they go to the wall. Rice Krispies I eat for breakfast, so I put Rice Krispies in. Sorry. So that's the idea, and there's a paper by Dominic Velle and Madovan, and it shows that if you have 2 particles on a surface, it doesn't matter whether or not the meniscus is caused by the chemistry or by the buoyancy or a combination. If the menisci have the same curvature, so the first and second diagrams, the particles attract. If you have opposite sign curvature, then in fact they repel. And so if I think of our lubricant surface in their very simple way, I'll forget the roughness. It's the fact it's on an oil and therefore drawing the oil up to make a meniscus. If I put a topographic feature in, then I have 2 meniscus. And if they overlap, they'll attract. Of course, 2 droplets might attract. So this is a droplet form of the Cheerios effect. And that's really what we did. So experimentally, you take something like a silicon wafer, but some kind of substrate. You put down a photoresist, a polymer. You remove some of the material. You put a coating on to create a superhydrophobic surface. And then what you do is you impregnate oil in and convert the superhydrophobic surface into one of these lubricated surfaces. You've got different length scales, the thickness of the oil. You've got the height of the step there. You've got the length scale for the meniscus. And if you look from the top, what we did was create a groove, so to speak, constant uniform depth, but in a V shape. This is a top view schematically. And that's what a droplet will look like on the top. That is a picture from the experiment. And then if you put the droplet on, you see that the droplet just moves to a particular location. The video is on repeat. And that's because you have menisci at the edge. Those menisci are going to define a stable position, but they also define how the droplet is transported to that menisci. And in fact, if you do this experiment and think about a phase sort of diagram, you can come up really with 3 different positions. You can start with one, where a droplet is so far away from edges, it doesn't see them because of the menisci. You have 2-dimensional translational possibilities. You can move around the plane. But if you move too much towards the top there, the menisci of the wall pulls the drop in onto the wall position 2. Then, of course, you can translate along the wall, but it's hard to come off. If you translate along the wall towards the apex, you pick up the second menisci from the bottom wall, and that actually pulls you into position 3. And if you start further into the apex, you're driven to it. And so you can see this is a video on loop, just showing it being pulled in. That's one on the wall, that's one there, being pulled to a position, that's pulled to a position there, and that's just showing. And so you've really got 2 local equilibrium, and then you've got, with 2D and 1D translational energy invariance, and you've got a global equilibrium in there. You could design where that equilibrium position will be by altering your opening angle of your wedge, altering your depth, altering the size of the droplet. So topography can be used. You could do a phase diagram, and that's in the soft matter paper. Another idea, somewhat different experiment. Let me take a plate that is super slippery, and let me take a second plate that is super slippery and form a wedge in this form. So a different experiment. Normally, if I do that with something like a super hydrophobic surface, as I press the plates together, the droplet moves away from the apex. Always does that in that configuration, never moves in. If I take a super slippery surface, then as I move the plates up and down, the droplet moves both directions. Doesn't always move out, sometimes moves in. And so you can get motion in towards the apex. If you think of a droplet, when I think of droplets on surfaces, I usually think of the droplet conforming to the surface. But if I think of a spherical droplet, I can think of cutting it and taking a cap out, and that's another way of thinking of the droplet. If I think of a droplet within a wedge, I can think of doing 2 cuts that take 2 caps away to give the droplet that's in the wedge. That's a really useful way of thinking. And the reason it's useful is it tells you about what I call energy invariance. If you think of the interface as giving you the energy, then I can think of making those 2 cuts in any orientation. And I won't alter the energy, because I'll still have the same spatial areas. But of course, if I change the angle of the cuts, if I propagate those cuts down to an apex, I've put a droplet into a wedge. And according to where I make the cuts, really what I'm doing is saying the droplet is in a different position within the wedge. And that's a way of thinking. So that's the idea there. So if I was to try to stop this at a particular position, which I can't in this one, then I will be able to show that you can therefore have a droplet transported in a wedge without altering its surface energy. And if you look at that, then you can draw a free energy diagram versus position. And what you show on the bottom here is that as you change the opening angle of your wedge, you move the drop to a different position further out, but the surface free energy doesn't change. The other one tells you it does change if you try to do that with the contact angle. You can think of moving the droplet by suddenly adjusting either the angle or the separation. If you change the separation, you're effectively altering where the apex is. And there are really 3 types of dissipation we might consider as a droplet moves. And actually, you can look at that in terms of an overall friction coefficient. And if you're moving close to your minimum, you can think of having a harmonic oscillator. You have just a bottom of a well. You just do an expansion near that. And if you've really got this super slippery surface and you do the change very slowly, then really you should lose 2 of the 3 contributions to the energy. You should just get, hopefully, just the hydrogen outflow in the bulk causing the friction. So you can do the experiment. So here we have a droplet in a wedge looking sideways. You suddenly move the plates. So you either open the angle and move them apart, and then you wait and see where does the droplet relax to, you measure the position, and you get an exponential relaxation to the new equilibrium, and you can fit that and therefore obtain the relaxation time. So in summary from this work, I guess my first message is it is actually relatively easy to fabricate surfaces on which you effectively remove the contact angle hysteresis. Gabby said that as well. You can see a Cheerios effect, you can think about that, and that allows you to think about positioning, controlling, transporting droplets. And actually, you can think of reconfiguring boundaries and making flexible boundaries that will transport liquids, droplets, around with virtually no loss. And with that, I'd like to thank collaborators, in particular James and Elfigo, the students who did the work. Thank you very much.
Out of curiosity, in the unit talk, you were showing droplets on these these informated surfaces where you have the droplet sits on top of the surface, and other cases where the droplet is entirely coated.
Yeah.
For what cases does that happen, and how do you diagnose it?
Okay. So I guess the first one is that work showing that comes out of MIT, and essentially Gareth McKinley and Chris Varanasi have done that. And so there's a whole set of questions about the balance of the different interfacial tensions. There's a set of equations to predict it. People have tried to image it, but it literally can be a monolayer. And so that has been imaged. And there's a group in Germany, Hans-Jürgen Boots, Doris Vollmer, have done some imaging to show some of that working.
What sort of images?
I'd have to go back and look. Okay.
Good afternoon, everyone. Today I'll be talking about the receptivity of supersonic boundary layers over smooth and wavy surfaces to impinging slow acoustic waves. To begin with, I will talk briefly about the role of receptivity in the transition to turbulence. Actually, it was Morkovin and Rychotko, the first one who coined the term receptivity, and they define it as the process by which external disturbances enter the boundary layer and excite instability modes. These instability modes can get amplitudes way larger than the ones in the beginning, and eventually leading the flow to transition to turbulence. So there are a few studies in the literature of the receptivity to both sound and wavy waves. Concretely, there are some experiments by Shapiro, Kashanov, and Sarek and White, and more recently, some DNS studies by Balakumar and Detuli and Rubin. On the more theoretical side, I will mention a couple of papers as well. The Rubin-Goldstein theory is the most famous one, which describes this whole problem. And another very surprising study is the one by Wu in 1999. He actually considered the generation of TS waves by convective gas and interacting with sound without any kind of roughness. And he found that this scale conversion can be achieved without any kind of roughness, which is very surprising. And actually this work, the work I'm presenting today, builds up on this study. So we will consider two different scenarios. In the first one, we will consider only sound waves, two sound waves interacting with each other alone. And the question here that we want to answer is, can the interaction of two impinging waves alone, as I said, produce a forcing able to excite TS waves? So the answer to this question is no, we need a roughness. That's what the Goldstein and Rubin theory tells us, because the roughness basically fixes the length scale of the TS wave. But we will find in this study that this is possible if the phase speed of the acoustic wave is what I called in the beginning slow, that is of the order of Reynolds to the -1/8. In the second scenario, we will consider a very classical problem, which is receptivity to basically sound and roughness. This problem has already been considered in the literature, and what we want to answer here in this study is by choosing the sound wave to be to have this phase speed, this slow phase speed. So we want to compute the strength of the forcing and compare it to the literature, we will see that it's stronger than the one computed in the literature for these slow sound waves. So here, what we need to do is to rescale the wave numbers and frequency, Reynolds to 3/8 and Reynolds to 2/8. The key point here is the scaling for the frequency, because this is different from the literature. In this way, it leads to a phase speed of the order of Reynolds to the -1/8. Also, for both problems, sound and sound roughness interactions, some resonance conditions have to be fulfilled. And so we are now ready for the triple deck problem, to formulate the triple deck problem. I will skip most of the equations because they can be very tedious, and I think we will lose the essence of the problem. What you have to know is that we are considering basically standard triple deck theory. That is, we decompose the flow field in 3 different decks, so-called decks, sitting on top of each other. A main one for the main part of the boundary layer, and on top of that, that's the upper deck, and then a lower deck as well. So here I'm showing, as an example, what the equations look like for the force response of the lower deck. We have taken asymptotic expansions for every probe variables when the Reynolds number goes to infinite, by the way. Here you can see on the right-hand side that there are terms coming from the TS wave, and also what is called their N1 and N3, which are nonlinear terms coming from the sound wave itself. So in the asymptotic expansion, we have 3 different kind of terms. The ones for the leading order terms, which are the sound wave. Then there is the terms for the TS wave, which is the eigen solution of the equations, and then the force response that with the subscript 2. For the sound roughness problem, we will have another extra term which accounts for the mean flow distortion by the wall roughness. So from these equations from the lower deck, plus the boundary conditions, we get to an equation for the amplitude, in which sigma and n are a function of the initial parameters of the problem, the 3 parameters of the problem, frequencies, wave numbers, Mach numbers, etc. And by matching this TS wave solution with the upstream force response, we get to A infinity, which is related to the coupling coefficient in 11 and 12 for both the sound-sound interaction and the sound roughness interaction. You can see in 11 and 12 the actual strength of the receptivity, which goes as Reynolds to 9/16 and 5/16 for the sound roughness case. Here you can see some parametric studies, some plots for the parametric study. On this figure, you can see the coupling coefficient computed versus alpha and beta, the streamwise and span-wise wave numbers, for Mach number 1.2 on the left and 4.5 on the right. So as you can see, if we choose omega to be of the order 10 to the -1, which is the case, we get the maximum of the coupling coefficient at also alphas of the order of 10 to the -1. Which is consistent with everything we are doing here, because the phase speed we are taking it to be of the order 1. I mean, it's C hat. So if we then increase the frequency to be order 1, in particular omega equals 3, then we get the maxima attained at alphas of the order of 1 as well. And here I am showing some results for the sound roughness problem. So as you can see, the coupling coefficient is plot versus C, and no clear tendency is really seen as we increase beta, the span-wise wave number. So as a summary, with suitable frequencies and wave numbers of the sound waves and roughness elements, the TS modes are excited near the lower branch of the neutral curve, which has a triple deck structure. expressions for the coupling coefficient have been derived and a parametric study has been performed. And probably the most important consequence of the choice of scaling is that order epsilon fluctuations in the free stream generate much larger, a factor of Reynolds to 1/8 velocity signature in the lower deck. We found a higher efficiency of the mechanism. In particular, for the sound case, we compare the strength of the receptivity found here with the one with Wu 1999. And it's about the factor of Reynolds to 1/4 larger. And for the sound roughness case, which, as I said, has been already studied in the literature, the factor is Reynolds to 1/8 larger as well. So with this study, I am encouraging more experimental and numerical studies because for this really particular regime of the slow acoustic waves, I don't know of any studies yet, so, and not DNS at all either. So, so that's it. Thank you.
So are there questions? The higher maximum is a direct resonance mechanism.
Sorry?
The higher maximum is there's a direct resonance mechanism that Fedorov has explored. How does that relate?
Well, the Fedorov theory is mainly for what's called the boundary leading edge receptivity. So in this problem, yeah, I didn't say it, but in this problem, we are considering that the roughness is farther downstream.
Any further questions? So then let's thank the speaker.
Thank you. Hi, so actually my name's Jay, yeah, so I've recently joined the group at Manchester Metropolitan studying boundary layer stability on rotating cones. Zahir was meant to be giving the talk today, but unfortunately he couldn't make it, so you're stuck with me instead. So this work was done by Zahir in collaboration with Professors Stephen Garrett at Leicester and Sharon Stephen at Sydney. So first of all, why boundary layers? Well, we all know that boundary layers are one way of attacking the problem of what happens in the transition to turbulence, and turbulence is a big problem in a lot of industrial contexts. So our focus really is on sort of kind of aerospace applications, so things like the nose cones on turbofan engines and spinning missiles, that kind of thing, is where we find cones and where turbulence is going to be a problem. So let's have a look at what kind of flow features we expect to see. There have been a number of experiments done over the last number of decades, and this is the kind of flow structure that we see. Broadly speaking, we can split up the flow into three pieces. We have a laminar region. Don't know if that's a laser. Yeah. So a laminar flow near the nose, the tip of the cone, followed by a region of instability where vortices appear to be shed into the flow by the boundary layer, followed ultimately by a region of turbulence after the vortex structure breaks down. And it turns out that this kind of structure is what occurs no matter what the sort of half angle of the cone is, no matter how broad or how slender the cone is. There's always some sort of rotation rate at which this happens. So I'm going to lift the veil just a little bit and say that even though we qualitatively see this kind of structure, vortices being shed into the flow, there is a difference between slender cones and broad cones. And I'm going to return to that at the end of the talk, but for now I'm just going to focus on broad cones. So if we have a look a bit more carefully at the broad cone situation, as I mentioned, you can see a similar structure. We have a laminar flow followed by the appearance of this vortex structure, where the vortices are swept around by the rotation of the cone, and then that's followed by a turbulent region. And if we zoom in a little bit and have a look at the vortex structure as the fluid gets rolled up into it, we notice that for broad cones, the sense of rotation of the fluid is the same in each successive vortex. So we have co-rotating vortices, and it's indicative of a cross-flow instability mechanism causing this vortex structure. So that gives us sort of handle on how to approach the problem asymptotically if we're looking for what instability waves are causing this vortex shedding. So if we move on, at this point we can sort of introduce our mathematical formulation, the geometry of the problem. So simply we just have a cone of half angle psi that's rotating at some angular frequency omega. Now in terms of our sort of boundary conditions, we have the flow being dragged around at the surface of the cone due to this rotation, and that's going to be given by omega x sine psi. And sort of if we have an axial flow, which I should have mentioned earlier, obviously in the case of a propeller or a turbofan or a missile, you're going to have some sort of axial flow. So it's useful to have this parameter in there. So introducing an axial flow, the slip velocity is going to take the form of a power law. And this lets us, when we non-dimensionalize, introduce a sort of a ratio for the importance of these two different flow speeds. So broadly speaking, small values of S are going to correspond to flows where the axial component is more important, and large values of S are going to correspond to situations where the rotation is far stronger than the axial flow. But yeah, so, and then obviously the psi is one of our other input parameters. And what we get to hopefully get out of this is some way of predicting the wave number of the vortices that we see in the structure that comes about as the instability develops, and the angle that this makes with the cone's meridian, because we can't assume that the spirals are simply just going to be aligned with the cone. They might occur at an angle. So those are our two parameters that we hope to model or explain asymptotically. So our procedure is pretty familiar to everyone, hopefully. We take a basic flow profile that we compute using a method that's appropriate. So in the case of no axial flow, actually, the equations with our non-dimensionalization collapse to the von Karman ODEs, but with an additional equation for the pressure. And if you have an axial flow, then we solve the boundary layer PDEs. And I think at the moment the code that we're using uses the Keller-Box scheme and method of lines to get that. So once you have your basic flow profile, you do the standard thing. You take a small perturbation. You assume that it has some sort of wave structure, and you perform your asymptotic analysis to see if you can describe the instability waves that should result. And it turns out when you take this, so specifically for the broad cone, we have a bit of a helping hand, because there's a lot of known work on the rotating disk, which actually does exhibit the same kind of vortex structure due to a cross-flow instability. So we already know a little bit about how to attack this, and it turns out that when we do the asymptotics, there are two modes in particular that we can see. One of them occurring as a result of essentially a Rayleigh equation in a layer that's, I think, 1 over root Reynolds number in size, and then another layer that's actually closer to the wall. So it's a viscous wall layer instability mode there, which is in a thickness that's 1 over Reynolds to 2/3, I think. So attacking both of these asymptotically, we can get some results. And if instead of doing that, we simply just discretize the equations, the eigen relation, we can find numerical solutions as well, and hopefully compare the two. So I've got some plots here now of neutral stability curves that we generated as a result of this asymptotic analysis and the corresponding numerical work. So just to quickly explain, the structure of these curves is quite clearly similar. So no matter what the angle of the cone, this cross-flow instability is there, and the numerics of these instability branches matches up very well with the asymptotics. These dashed lines represent the asymptotic results. And the only effect that we really see here is that as we increase the half angle of the cone, so we make it more broad, then the flow is stabilized ever so slightly, and the number of potential vortex wave numbers is reduced. So the flow is basically just becoming a bit more stable. And if we have a look at the wave angle associated with these vortex tubes, so the angle at which the spiral is oriented with respect to the cone, we can see that as the cone half angle increases, this gap here grows, which means that essentially the vortices are spiraling at more and more of an oblique angle compared to the cone, which makes sense because as you get a broader cone, you have greater rotational shear force because of the rotation of the cone, which drags the vortices around. Beyond that, so this is just a new version of the stability, numerical stability codes that we've got using a spectral method, decomposing the hydrodynamic functions in terms of Chebyshev polynomials. You have to trust me that these curves do actually go along and match up perfectly well with the asymptotics. I just didn't have enough time to run this. But okay, so a couple of slides here just to show that we do. So these are basically portions of the neutral stability curves that we had, and compared with some experiments. So the black lines here are actually the new spectral code. The red lines are the old numerics for the instability, and this blue is Kobayashi's results from 1980 odd. And there's a reasonably good agreement between the numerics, asymptotics, and the experiments here, except we see some interesting feature here around psi equals 40, where the agreement definitely reduces for smaller angled cones. And if we compare, so there's a critical Reynolds number for the appearance of these vortex tubes, and for the most part there's good agreement. Like you can pick up these different instability modes pretty well. This experiment is, we reckon the experimental setup was flawed. But yeah, so moving on, the important feature really here is that at some angle we have a discrepancy between our prediction and what's going on. And it turns out that this is where the slender cone comes back in, and we have a bit more of a complicated, sorry, not a bit more complicated, a different mechanism entirely that causes the vortex structure. So we still see the vortex structure, but if you zoom in, instead of co-rotating vortices, you see counter-rotating vortices, which is instead indicative of a centrifugal mechanism. So you can turn the handle again and do all the asymptotic analysis, etc. And this was done, and they've succeeded in basically explaining that mechanism too. So we have a good model for what goes on with the slender cones and with the broader cones in terms of the appearance of this vortex structure and what causes it. But in terms of ongoing work, what we're trying to do is explain what happens in between, because there is a crossover, there's a handover of the dominant instability, and our question is exactly, can we use that information to guide us in sort of designing components of nose cones and stuff. Anyway, I'm done. Thanks.
Any questions?
What condition do you impose where you break your computational domain?
Where break the sorry, at the.
So you've got the tip of the code.
Oh yeah.
I guess at some stage you have to say whether stop. What sort of condition do you impose on that?
So actually, I think the code. So disclaimer: I've literally just been given the code for this. On Friday. So I think what they're doing is actually a quasi one-dimensional analysis based on their non-dimensionalization takes out the x dependence of the flow. So it's a quasi 1D thing at the moment, but I'm hoping to take a closer look at that.
There are some words regarding, it's a similar model there we call it the Göttingen vortices.
Yeah.
And is it like similar topology when you do like decomposition or?
Exactly, yeah. So so for the slender cones, I didn't present any of this stuff, but if you zoom in here and you look at the similar stuff to this, you see a vortex tube going that way and another one going that way, exactly like how you see with the vortex, or with the Gortler vortex.